Welcome back. Today, we're going to talk about the topic of estimation in statistics and the related concept of statistical inference. We're really just going to introduce some ideas today about estimation, which we will follow up on later because there's a lot to say about estimation in statistics. But today, we'll get a bit of an overview. So, first of all, we're starting from this term statistical inference, and we'll have a bit more of a fleshed out definition in a moment. But let's talk about what motivates the idea of estimation, the idea of statistical inference. Well, even though when we're doing research, when we're working with data, we usually only have a limited sample of data, we're often interested in drawing conclusions that go beyond that data that we have in front of us. And we'll have some tangible examples in a moment. But one motivating framework for this is thinking about causality. And often when we discuss causality, we're going to use this term counterfactuals, which we'll define in just a moment. But part of the idea for causality is that we want to be able to make statements like, if A happens, then B is going to follow. Well, that actually requires speaking a little bit beyond what the data in front of us says, because we need to be able to talk about actual causes, cause and effect. And one of the ideas behind cause and effect is that if A happens, then we'll see B. If A doesn't happen, we won't see B. But we only get to observe the world one time, right? We can't observe what would have happened if A didn't occur. So in trying to talk about this, we can get a little bit philosophical, but this term counterfactual is going to be really helpful for us in talking about what we mean in terms of causality. Counterfactual refers to a hypothetical alternative to what actually occurred, where one or more independent variables takes on a different value. And if you'll recall, we said that independent variables are usually the kinds of variables that we think about causing some other variable, the dependent variable. So it makes sense that we're wanting to think about what would have happened in a hypothetical world where we had tweaked or changed the values of the independent variables. What would have happened to the dependent variable? That's the kind of thing we're thinking about when we talk about counterfactuals. You could think about this as being like alternative universes where everything's the same except for one factor has been changed. That's the kind of thing we're thinking about when we say counterfactuals. And that's also why I say this is speaking beyond the data in front of us, right? We're thinking about what ifs. Here is another example is that we can think about doing an experiment where we give one group of individuals, for example, a treatment, maybe a medication that we're testing out, and then another group we give a placebo. So we would say we have the treatment group and the control group, and we're wondering what would have happened to the treated individuals if they hadn't been treated, if they'd gotten the placebo instead. That's a counterfactual. And conversely, we might wonder what would have happened to the control group participants if they had received the treatment, right? We're wondering about these counterfactuals. What is the actual causal effect of the treatment? The language of counterfactuals is going to help us discuss that very precisely. So, if we zoom out a little bit, we can say that statistics basically falls into two broad categories. First is descriptive statistics, which is what we've mostly been focused on up until this week in this course. And descriptive statistics are just using statistical figures or numbers, things like the mean, the mode, the median, right? Using statistics to describe or summarize information about data that we've collected, right? We might have a data set and it has many rows of data, and so it doesn't make sense to go through and read every row of data. Instead, we want to be able to summarize it, to describe it. And statistics helps us to be able to create concise summaries of a lot of information, right? That's one purpose of statistics, which we call descriptive statistics. Inferential statistics, this term that we started kind of using since the beginning of this lecture, but haven't defined up until now, a very precise definition of inferential statistics is that we use inferential statistics to draw probabilistic conclusions about something. Now, I give you two possibilities for what we might be drawing a conclusion about. One could be a counterfactual. In other words, we're drawing a conclusion about causality. What would have likely happened if something was different in our sample, if the values of the independent variables changed? what would we likely observe, right? That's a probabilistic conclusion that we can reach using inferential statistics. Second type of conclusion we might reach with inferential statistics is drawing a conclusion about a population based on a smaller sample that we've collected, right? Maybe I talked to 1,000 individuals in the US, but I'm trying to estimate what is the view of the entire US adult public, right? But I have just a sample of 1,000 people that I talked to. That process of trying to draw a conclusion about the population from the sample is going to rely on inferential statistics. So we will talk more about both of these concepts, either trying to draw a conclusion about a counterfactual or about a population, as we proceed through the lecture. But that is what we mean when we're talking about inferential statistics, trying to draw probabilistic conclusions about one of those things. So, one important thing to note about statistical inference is that there's always going to be uncertainty. We can never learn the full truth with 100% precision or certainty. Thus, statistical inference is all about estimating, hence the title of this lecture, that it's about estimation. All right. So both fields, inferential and descriptive statistics, use formulas to compute statistics that are going to help us learn about whatever data we're interested in. But the key difference, again, is that with inferential statistics, we want to be able to describe data that we don't have access to. We're going beyond the data in front of us and trying to draw a broader conclusion, whether that be a conclusion about a counterfactual that we don't actually observe or about an entire population, a larger set of units than those that we have data for. So let's jump into one of the practical tools of statistical inference, and that is confidence intervals. And we'll return a little bit later to some more description of how statistical inference works. But let's jump straight into a practical example, confidence intervals, which is an application or a tool that we use in statistical inference. So you've probably heard pollsters talk about the margin of error in their polling. When they use that term margin of error, they're essentially referring to a confidence interval. But we want to be a little bit precise in how we talk about confidence intervals, just trying to relate it back to a term you've maybe heard before. With confidence intervals, we're going to be able to make statements like, I'm 95% confident that the true population mean lies between 45 and 49, assuming that we've made accurate assumptions in our statistical model. And that caveat that we're always having to rely on assumptions in order to generate a confidence interval is going to be kind of important, right? And in this lecture, we're not going to go into the weeds and see what kinds of assumptions need to be made in order to be able to create a confidence interval, but we'll return to that in future lectures. But just know for now that in order to create a confidence interval, we have to rely on some assumptions about how the data is being created. And if we violate those assumptions, our confidence interval might be wrong. I also want to note that this particular interpretation of a confidence interval, saying I am 95% confident, that's maybe not 100% correct. That's an intuitive interpretation of what a confidence interval is. But some people will criticize it because technically, in at least the kind of statistics we're going to be talking about, a better interpretation might be that we're using a process that will give us a correct answer 95% of the time. In other words, the process is 95% reliable that in producing an interval that contains the true number. And confidence is something that is a bit more subjective, right? And in particular, we might have other sources of information in addition to just the data in front of us, like our intuition or prior studies that have been conducted. And if we're trying to say, how confident am I that something is true, we might want to bring that external knowledge to bear on that. So for that reason, some people will really criticize this kind of interpretation of a confidence interval. But my own personal opinion is that it's not a bad way to get started when it comes to interpreting confidence intervals, and that it's, I think, one of the most intuitive interpretations of confidence intervals. So why not start there, and we can fill in details later if we have desire to do so. All right. So confidence intervals, I just gave an example on the prior page where we say we're trying to estimate a population mean, right? An average, but we can also use confidence intervals to describe associations between two variables. In other words, not just the mean or average of a single variable, but we can talk about how two variables are related to one another. So let's look at an example of that. Let's say that we're wanting to examine whether or not gender is related to sentiments about the public, whether or not you approve of the public. And maybe we just have a sample of 1,000 people, but we're trying to draw a conclusion about an entire population, right? All of the public. And so this would be an example of where we want to do statistical inference. We want to create a confidence interval, make an estimation. So what we can do is we can create a confidence interval for the difference in average government satisfaction between men and women in the population. In other words, how much does approval or satisfaction, I guess maybe those should be distinct concepts, but I've treated them as the same for now. We have an average approval for men and an average approval for women, and we want to know what's the difference. Well, we can calculate an estimate of the difference, but we can also create a range of what we think a plausible difference is, a confidence interval using inferential statistics. So, for example, maybe we run the numbers and we find that the confidence interval is from 2 to 5. In other words, we're saying that we think it looks like average satisfaction is between 2 and 5 points higher on a 10-point scale for women than it is for men. That's the kind of thing that we can do with a confidence interval. Therefore, we would say it's unlikely that there's no difference between men and women. Notice that the interval of 2 to 5 does not contain 0, which would mean 0 would mean there's no difference, right? If the difference is 0, that's no difference. So between 2 and 5 doesn't include 0. So we'd say that there is a statistically significant or meaningful relationship between gender and satisfaction if we get a range like this, a range from 2 to 5. And we'll return to this concept of statistical significance in the future, but just introducing it now. You saw this term also before when we talked about regression, right? Significance, sign, and size. The significance refers to statistical significance. If instead we ran the numbers and found that there was a confidence interval of with a range of -2 to 3, notice that when we have start with a negative number and end with a positive number, that means that 0 falls within that range. Then we'd conclude that there's no statistically significant difference. In other words, it's very possible that attitudes of men and women are the same on average, right? That's what a range like this would indicate. So, again, we're not going into too much detail yet, just kind of giving an overview of what confidence intervals are and what kinds of things that we can use them for. So here's an example with actual data. So I want to know, is job tenure related to wages? In other words, how long somebody's been at their job, does that relate to how much they eventually make? And we're going to look at some sample data that comes, this data manual uses this data set to illustrate some of their features. And it's a sample of women in 1988. Wages are measured in dollars per hour. And keep in mind that wages were a lot lower in 1988 than they are now. And there's also been inflation since then. And job tenure is going to be measured in number of years. So you can see if you want to try this on your own, you should be able to put this into your Stata window. If you have Stata on your computer, you might actually have to add in HTTPS because there have been protocols that have been updated. Maybe I should have updated this link, but that's how the internet is evolving. And if you want to get a confidence interval, you might need to install this package because base Stata doesn't include an easy way to create confidence intervals for a correlation. After you've installed this package, you can then run this command. It's asking for the correlation confidence interval between wage and tenure. If you do that, you should get a result that looks like this. So this is maybe not the cleanest output in Stata, but I know that this first number is just what is the correlation between these two variables in this data set. So this is still in the land of descriptive statistics. It's just saying with among these 2,231 observations that we have in our sample, what is the correlation between age in dollars per hour and tenure, number of years that that person has been working that job. And you can see that the correlation is 0.178. So that's a positive number. That means that when tenure is higher, wage tends to be higher. But 0.178, that's a lot closer to 0 than it is to 1, right? The very maximum correlation that we can have. So we would say it's not a very strong relationship, but it's a slightly positive relationship. These next two numbers in this output, though, are going to give us that 95% confidence interval. So we want to think about this as a range of plausible values for what the correlation would be in the population, right? If we assume that these 2,231 individuals that are represented in this data set are a good sample to estimate about the whole population in the whole country, then we could say that for the whole country, we would expect that the correlation between wage and tenure among women would be something like this, right? Somewhere in this range between 0.137 and 0.218. That's a range of plausible values. And again, I've given this kind of quick and easy interpretation, which is to say that we're 95% confident that the population correlation is between these two values. But others would say maybe it's better to say the process that we're using will be accurate 95% of the time if we use it to calculate a range. And this is the range that we have. Since that range does not include zero, right? This is all positive values that fall within this range. We would conclude that a correlation of zero isn't particularly likely. Therefore, there's a statistically significant or meaningful correlation between wage and tenure. In other words, it does seem like higher levels of tenure are associated with higher wages, right? It's not just a fluke or that they basically have no relationship with each other. All right, let's look at another example of how to use inference. We looked at correlation just now, but let's think about regression. We already learned, like I said, a little bit about regression because we learned how to say whether or not a coefficient was statistically significant in the previous lecture. But let's add a little bit more information to that story. So when we run a regression, we're trying to draw a line. And one of the ways that we can think about this is that we are estimating a model. And this should look sort of familiar, but there's a new term here that was not shown in the prior lecture, this Greek symbol. Um, and what this is going to represent is random noise with this Greek symbol epsilon. We want to make inferences, that's why we call this statistical inference, about this true model based on the data that we have in front of us. In other words, if we assume that the values of our dependent variable are caused by our independent variable, as well as other random factors that we haven't measured that we can't predict, then this is perhaps a model that exists in the world, right? The dependent variable is partially caused by the independent variable as well as other factors, but we can only imperfectly measure this relationship between the independent and dependent variable because we aren't able to measure all of those other factors, right? But we can, under certain assumptions, make a pretty reliable estimate of the relationship between the independent and dependent variable, even if we can only make an estimation. We can't know for sure the exact truth. We can create a good estimate under certain conditions. So we're going to describe that estimate using these two main tools of statistical inference, either confidence intervals or significance tests. And we'll talk about significance tests in more detail in a future model or future lecture. All right, so for each coefficient, data output will show us a p-value in order to let us decide if we can reliably conclude that there is that a coefficient is non-zero, right? And that's what we learned about last week when we said we were going to look for significance of the coefficient. If the slope is non-zero, in other words, if b does not equal zero, then x and y are related. If b is equal to zero, then that means there's no relationship between x and y. This p-value, this significance test, we're really asking the question, is it plausible that there might be no relationship between x and y? In other words, is it plausible that b is equal to zero, or can we kind of rule that out, that b is probably a number other than zero? Data output will also show us confidence intervals for each regression coefficient, in addition to the p-value that we focused on in the previous lecture. So let's see an example of that. We're going to continue to work with this same data, but now instead of running a correlation between these two variables, we're going to run a regression. And you can see this is the kind of output that we get from Stata when we look at this data. You can see it's the same number of observations as before, the same data that we're looking at. But now instead of seeing a correlation coefficient, we see a regression slope coefficient right here. And we have a p-value like we talked about last time. Now, since this p-value is less than 0.05, we're going to say that it's statistically significant. And we'll have that on the next slide, I believe. But right here, you can see that we also have a confidence interval, which we didn't look at last week. In other words, if we want to give this quick and easy interpretation of confidence intervals, we would say that we're 95% confidence that the true slope coefficient is between 0.14 and 0.23, between these two numbers that are displayed right here for the slope coefficient, right? The coefficient that comes next to tenure. And you can see that this point estimate that we focused on before is right in the middle of that range. This number is going to fall right in between this range of two numbers that we see over here for the confidence interval. So in other words, if we want to try to make sense of these two numbers, well, $0.14, that's 14 cents. $0.23, that's 23 cents. So we could say we're 95% sure that an additional year on the job typically corresponds to a raise or an increase in wage that is between 14 and 23 cents. As we talked about briefly, the p-value is less than 0.05. So we're going to say that it's a statistically significant relationship. And also because the sign here is positive, we're going to say that it's a positive relationship. In other words, even after we account for random noise in the data, we're confident that tenure truly has a positive relationship with wages. That's another way we can interpret that. All right, last topic that we want to talk about in this lecture is a little bit about sampling. You can teach, we could have several lectures on sampling, so this is just going to be a very brief introduction, but it will be helpful to us going forward. Statistical inference is usually taught in most stats courses through a discussion of sampling. So let's go over some simple or core sampling concepts. Population, we've used that term already in this lecture, but here's a formal definition: the universe of units that you're interested in learning about. For example, maybe we're interested in all eligible voters in the US. But the question is, are we able to go talk to every single eligible voter in the US if we want to do some data collection? No, we can't. That would be too expensive. And even if we tried, we probably couldn't get everyone to talk to us, right? And so, because recognizing that it is sometimes not possible to observe or collect data for the entire population of interest, we are going to often collect a sample. Although, if it is possible to observe everyone, then we call that a census rather than a sample. So, census is a term that means we've talked to everyone in the population, whereas a sample is what we use when we aren't able to conduct a census, when we can't talk to everyone in the population. And in that case, sample refers to the actual units you observe that you have data for, right? So again, units, that could be individuals, that could be organizations. It depends on the particular research context. But in this case, we're talking about individuals, right? With this example of eligible voters. Maybe we're only able to talk to 1,000 of them. So we would say that those 1,000 that we talked to in our survey would be our sample, whereas our population is all eligible voters in the US. All right, so that's a very simple example, but in practice, sometimes defining the population is a bit tricky because we might be interested in more than one population, or as the textbook talks about, there might be a hypothetical population that we're interested in, right? So sometimes instead of talking in terms of counterfactuals, we might talk about a hypothetical population, those that didn't receive the treatment, for example. So just one example of how this might come to be, where it's hard to define exactly what the population is. Let's say I'm interested in studying racial attitudes and I have a sample of 1,000 US adults who were interviewed in as part of a survey. I might be particularly interested in the current attitudes of all adults living in the US, not just the 1,000 that I talked to. So I could say that that's my population, all adults living in the US. However, I might also be interested in, to some degree, in the broader principles of human behavior, right, that extend beyond the current attitudes of all adults living in the US. In other words, I might be interested in general social science theory that could describe individuals in other countries and also in different time periods, that could help explain how Americans feel not just today, but 100 years ago, right? Past and present. So in this case, it kind of begs the question, am I really interest is my population really all adults currently living in the US or current attitudes of adults living in the US? Or is my population more like all humans across time and space? Because of this, it's not always easy to precisely define what our population is. And if you read a lot of social science research, they may not say exactly who their population is in the study. And implicitly, they may sort of imply sometimes that they're interested in one population, and then another passage may be talking much more broadly, right, about a bigger population. And so it's not always super simple to figure out exactly what population people are interested in just by looking at their sample and their how they describe their research. So just know it's useful conceptually to distinguish between a population and a sample. But in the real world of research, this distinction sometimes gets a little bit messy and unclear. All right. So let's talk about different kinds of samples, different ways you can create a sample. So the sort of classical type of sample is what we call a probability sample. The simplest version of which is just a simple random sample. And this describes a sample selection method, meaning how you decide who to put in your sample from the population. That sampling method relies on random selection of people into the sample. Um, the reason we say use of randomness is that random selection is going to be easy to model. We're going to have mathematical formulas and things that line up really nicely, and we can create confidence intervals that make a lot of sense. For example, if we grab a sample that was selected randomly, right? We can model that. Whereas if we have individuals who like opted into the sample or something like that, it wasn't a random process, that becomes very hard to model. To know how should we construct our confidence intervals. So it's sort of a mathematical convenience to rely on this assumption that we pick people randomly. In the real world, if we try to do random sampling, what this often looks like is maybe we have like a list of people who are registered to vote in a particular county. Sometimes you can go and request that information from the county. You might have to pay a fee or something like that. But it's often public information, right? Meaning that the county, it's not confidential. If you pay the county, they'll be willing to give you the list of registered voters in many locations. So we could go get that list from the county and then use a random number generator on a computer to select which 100 individuals from that list of maybe thousands of registered voters we want in our sample, and then we have to find a way to go try to contact those people. um, Another example could be what's called random digit dialing. So this is maybe becoming a little bit less common, but it used to be a common method of conducting surveys where you would sort of have a random number generator, a computer or something like that, that would just select a random set of numbers, and then you would dial that number. Maybe you would systematically pick the first few digits to make sure you're getting different area codes and things like that. But at least the last four digits of the number would just be randomly selected. You try calling that number. Maybe it's been disconnected, right? And then you just try again. But the idea there is that you're just randomly picking different phone numbers to call, and that way you have some assurance that it really is sort of random who ends up in your sample and who doesn't. We're going to talk about some caveats to that in a moment. All right. Maybe the opposite extreme from a random or probability sample is what we call a convenience sample. This is where units are included in the sample because of convenience rather than random selection, right? So this could be something like I ask my friends. They just are convenient. I already know them. I have their contact info. So I just contact them. I select them for my sample because of convenience. Or these people volunteered, right? We just asked, does anyone want to be a part of the survey? And these are the people who stepped forward, right? That's a convenience sample. A third term that gets used sometimes is what's called a representative sample. And this means that units are selected such that certain known demographic characteristics, maybe race, age, income status, or level of the sample are going to resemble the broader population. So, in other words, maybe you want to make sure that your sample is 50% men, 50% women, because you know that's approximately what it looks like in the population, right? So you only reach out to 50 men and 50 women for your sample to try to make sure that it's balanced, right? So often the term representative sampling is used to refer to some sort of convenience sample, but instead of just saying I'm going to, contact all my friends, instead I say, okay, I'm going to deliberately contact people in a way that I know that I get demographic diversity that sort of mirrors that diversity that we see in the public, for example, mirrors the proportions we see in the general public based on census data or something like that. The purpose of representative sampling is that you're hoping that this is going to lead to better ability to be able to draw conclusions about a population from the sample, because you know on these particular characteristics that you've been able to measure that your sample mirrors the population, that it resembles it. But this is a little bit less exact and precise than um, than probability sampling, which is where we have clear mathematical models for how to describe our confidence intervals and things like that. All right, so in the real world, no sample is perfect, and often it's going to be a mix of random, representative, and convenient sampling. There's a few reasons for this. One of them is non response or missing data. So even if I have a voter list and I randomly select 100 people from that voter list, if I go and try to reach out to those 100 people, some of them are going to say no, I don't want to answer the survey, right? Or if I show up at their door, they might not answer the door. They might not be home even if I go to their door 3 or 4 different times, right? I could try calling them and they might just not answer no matter how many times I call them, right? So because of that, even if we start from a random sample, by the time we have to weed out all the people who refuse to respond or who have missing data for other reasons, we end up with a sample that is not purely random, right? Some people sort of opt out of the survey, even if we randomly picked them to be a part of it. And that's something we would kind of put under the category of convenience, right? Who actually happened to pick up the phone versus who didn't. It was just convenience that these particular people picked up the phone. So that means that even though we often start with trying to get a random sample, it's very difficult to achieve a purely random sample. We often have a mix of random and convenient sampling, and maybe we make some efforts to try to make sure that the sample at least looks representative. The more closely, though, that a sampling process resembles the random selection process, which is typically going to be the basis of the assumptions we use in our statistical models to compute confidence intervals and things like that, the more closely the actual process resembles our assumptions of randomness, the more confidence we can have that the conclusions of our statistical models properly describe our sample. But this is not an exact thing. It's very hard to quantify, for example, how closely we come to mimicking those assumptions. So, therefore, this is something that's going to require some subjectivity to kind of assess, right? Does it look like the way that the sampling was actually carried out in the real world pretty closely resembles a random process, or was it very much more of an opt-in kind of thing where the people who opted into the survey might look very different than the people who didn't opt into it? So, that again is just a brief introduction to a bunch of really important topics in statistical inference, right? We learned a little bit about confidence intervals, we learned a little bit about counterfactuals, and we learned a little bit about sampling. But there's much more we could learn about each of these topics. This is just kind of a broad overview, but hopefully it gives you a little bit of an idea of this really core piece of statistics, which is trying to go beyond the data in front of us and draw broader conclusions about the world from that finite data source that we have.